All right, we're going to continue our discussion on chapter 6, exponential functions. For any real numbers a greater than 0 and a cannot be equal to 0, the following statements are true. A to the power of x is a unique real number for each real number x. When we have a to the power of b is equal to a to the power of c, when the base are the same, then the exponents must be the same. So a to the power of b is equal to a to the power of c if and only if b is equal to c. We're going to use this property here where we can make the base the same and then let the exponents equal each other to solve equations. When m is less than n, if and only if a to the power of m is less than a to the power of n, provided a is greater than 1, m is less than n if and only if a to the power of m is greater than a to the power of n, provided a is between 0 and 1. We're going to look at some examples. If a greater than 0 and a is not equal to 1, then f of x is equal to a to the power of x is the exponential function with the base a. Here we want to graph f of x is equal to 2 to the power of x. Determine the domain and range of f. This is where a is greater than 1. We can make a table. So in this case, let's say if x is equal to 0, x equal to 0, 2 to the power of 0, anything to the power of 0 is equal to 1. So you can see your graph gonna passes through this point 0 and 1 right there. And as you increase x to x is equal to 1, would be 2 to the power of 1, which is equal to 2. So when x is equal to 1, y is equal to 2. As you can see, this function exponentially increases as you increase the value of x. So this is how the graph would look like. And as you decrease the value of x, you see the graph going to get closer and closer to 0. So these are the basic graphs that you want to keep in mind, put in your summary sheet. So later when I add numbers to this to shift them up or down or right and left, you can use these basic graphs to use the shifting method to graph them. The domain of this goes from negative infinity to positive infinity because this is going to go to ever from left and right. However, the range would be from 0 all the way to infinity, not including 0. And you can use your graphing calculator to verify that. This would be an example where we want to graph a function when a, the base is between 0 and 1. In this case is 1/2. We want to graph 1/2 to the power of x and find the range and domain. We're going to set up the table. If x is equal to 0, anything to the power of 0 still would be equal to 1. So you can see at x equal to 0, y or g of x is equal to 1. So my graph going to passes through the same point again, 0 and 1. However, as I increase the value of x, because the base is 1/2, this function gets closer and closer to 0. As I decrease the value of x, you see this function exponentially increases. The domain would be the same, all the values from negative infinity to positive infinity, and so as a range still would be from 0 to infinity, not including 0. And we can verify all that using our graphing calculator again. So when f of x equal to a to the power of x, when a is greater than 1, the domain would be from negative infinity to positive infinity, and the range would be from 0 to infinity. And as you recall, we looked at the shape of the graph using manually or using the graphing calculator. As you can see, the domain and range are pretty obvious here, and you can see the shape of the graph. When a is between 0 and 1, as we saw previous example, you see the shape of the graph would be still going through point 0 and 1. However, as I increase x, the function get approached to 0. As I decrease x, the function exponentially increases, where you can see that using the graphing calculator. graph f of x equal to minus 2 to the power of x and find the range and domain. The graph of f of x equal to minus 2 to the power of x is the reflection of the graph of y is equal to 2 to the power of x across the x-axis. So if you look at y is equal to 2 to the power of x, you reflect that respect to the x-axis, that would be the graph of f of x equal to minus 2 to the power of x. You can see the effect of minus here then. The domain would be from negative infinity to positive infinity. However, the range would be from negative infinity all the way to 0. Here we have f of x equal to 2 to the power of x plus 3. You want to graph this and find the range and domain. If you recall, we know how to graph y is equal to 2 to the power of x. We looked at the shape of that. This would be the same graph, except you translate this 3 units to the left. So because we have x plus 3, we shift this to the left 3 units. If this were y is equal to 2 to the power of x minus 3, then you would shift this graph 3 units to the right. The domain would be from negative infinity to positive infinity, and the range would be the same from 0 to infinity. So we're using the shifting method to graph these. Here we have f of x equal to 2 to the power of x plus 3. This can be done by looking at the graph of y is equal to 2 to the power of x, and then shift this up 3 units. And as you can see, the domain would be the same. However, the range would be from 3 to infinity. If this were 2 to the power of x minus 3, then you would shift that graph 3 units down instead. Use a graph to evaluate 2 to the power of square root of 6. So we know what square root of 6 is equal to. You can use your calculator. Square root of 6 would be about 2.449487. So the graph of y1 equal to 2 to the power of x with evaluation of x is equal to radical 6 would give you the value for 2 to the power of radical 6. You could use your calculator or you can use a graph. As you can see, your graph shows that y would be equal to 5.4622288 when x is equal to this value, 2.449487. This is how you evaluate this using the graph. You can also evaluate 0.5 to the power of minus radical 2 using the same method. We're going to evaluate what minus radical 2 is equal to. Using our calculator, that would be about minus 1.414214. When you graph y1 is equal to 0.5 to the power of x, when x is equal to this value, we can find y1, and you can see y would be equal to 2.6651441, as you would get it using your calculator. Here we're going to solve this equation. The variable that you're solving for appears at the exponents. So x is right at the exponents, 25 to the power of x equal to 125. The goal here is to see if we can make the base the same. If I can make the base the same, then I can conclude that the exponents must be the same. And looks like we can make the base equal each other. One is 25, the other one is 125. So if you write 25 as a factored form, if you break 25 to its prime numbers, you can see that the same as 5 times 5, which is 5 squared. So in place of 25, I'm going to write 5 squared. In place of 125 also can be right as its prime numbers as 5 to the power of 3. So you can manage to make the base the same. So we have 5 to the power of 2x is equal to 5 to the power of 3. So we can write this as the base the same as 5. If the base would be the same, the exponents must be the same. So we can conclude from here that 2x then must be equal to 3. We can only use this method for selected problem where you can make the base the same number. If I had 126 instead of 125, I couldn't use this method. So in this case, we get 2x is equal to 3, then you can solve for x. So x would be equal to 3 over 2. You want to verify that is true. 25 to the power of 3 over 2 is equal to 125. So yes, the solution is correct. This would be like the second root of 25 raised to the power of 3, if you recall. So that is the same as 25 to the power of 3 over 2. Remember, the number at the bottom of the fraction is your index. So that would be square root. Put the 2 here if you want to. That would be 25, then raise it to the power of 3. Square root of 25 is 5. 5 to the power of 3 indeed is equal to 125. You want to solve 1 over 3 to the power of x is equal to 81. Again, the goal is if we can make the base the same. So in this case, we have 1 over 3 is the same as really is 3 to the power of minus 1. You recall we had this property, if I have a to the power of minus n, that's the same as 1 over a to the power of plus n. Or if I have 1 over a to the power of n, I can move it to the top of the fraction, make it opposite sign. So that's what we're doing here. The exponents of 3 is 1. If I move it to the top of a fraction, it becomes minus 1. So here I have 3 to the power of minus x is equal to 3 to the power of 4 because 81 is 3 to the power of 4. So yes, we can make the base the same for this example. So we can conclude from here that minus x must be equal to 4. So from there we can find x is equal to negative 4. We can check our answer as we did before. Here we want to solve 1.5 to the power of x plus 1 is equal to 27 over 8 to the power of x. We're solving for x here. Now the goal is if we can make the base the same. Here we have 1.5 on the left hand side. On the right hand side, we have 27 over 8. It's not as obvious as the other example we did before. But what is 1.5? 1.5 is the same as 3 over 2. And I can write 27 over 8 as 3 over 2 to the power of 3. So yes, we can make the base the same here as well. So it looks like that the exponents now, which is x plus 1 in the left-hand side, must be the same as the exponents on the right-hand side, which is 3x. So we can solve this equation for x. X plus 1 is equal to 3x. To solve for x, you would get 1 is equal to 3x minus x, which is 2x, so x equal to 1/2 or 0.5. Again, we can check our answer by substituting a value to the original equation to verify the solution. We can substitute, or we can also use our graphing calculator to see where does this intercept. So if I input on my graphing calculator 1.5 to the power of x plus 1 minus, if I move this to the other side, becomes minus 27 over 8 to the power of x. If I graph this, so this would be equal to 0 if I move everything to one side of the equation. So if I go ahead and move these graph, we call it y1, being 1.5 to the power of x plus 1 minus 27 over 8 to the power of x. If I move everything to one side, that would be equal to 0 then. So you want to equate this to y is equal to 0. This would be y is equal to 0. So in other words, when you graph this function and you graph the equation y is equal to 0, wherever these two line and the graph intercept, that would be your solution, which looks like it's 0.5. That's exactly how we calculated manually. So the solution set would be 0.5. We can use the graph also to indicate where your function would be greater than 0 or less than 0. So from negative infinity all the way to this point, 0.5, the graph is above 0. And from 0.5 all the way to negative infinity, the graph will be below 0. So that's how you would indicate that. So from negative infinity to 0.5, the function would be positive just by looking at the graph. And from 0.5 to negative infinity, the function would be less than 0. Solve 3 to the power of 2x less than 81. This is an inequality. You're still going to see if you can make the base the same. So in this case, looks like 81 can be written as 3 to the power 4. Yes, we can make the base the same. So if the base are equal, then 2x must be less than 4. Then we can solve for x by dividing both sides by 2. So x would be less than 2. So we can use the same method for inequalities. So in this case, we have 1/2 to the power of 2x less than 1/16 to the power of x plus 3. The question is, can I make the base the same? Looks like we can. 1/16 is the same as 1/2 to the power of 4. The only difference here is inequality. So if the base are the same, then we can conclude from that the exponents 2x must be less than the exponents to the right-hand side, which is in this case 4x plus 12. When you distribute 4 by x plus 3, you get 4x plus 12. You just simply solve for this inequality by, in this case, you can subtract 4x from both sides of the inequality. You get 2x minus 4x will be minus 2x greater than 12. You have to be careful here. To solve for x, you have to divide both sides by negative. So you need to change the direction of inequality here. So here I change the direction of inequality here because I am dividing by minus 2. When you divide by a negative, then you would change the direction of inequality to its opposite direction. So x would be less than minus 6. Compound interest also can be solved by these exponential functions that we are looking at. So if you recall, simple interest was I equal to the principal times rate times time, PRT. If A is final balance at the end of each year, then in first year, A would be equal to P plus PR, which is equal to P, if I factor the P would be P times 1 plus R. Second year, this would be A is equal to P times 1 plus R plus P times 1 plus R times R. So as you can see the pattern here, this would be P times 1 plus R to the power of 2 for the second year. For the first year was P times 1 plus R to the power of 1 because this was first year. So for the third year would be P times 1 plus R to the power of 3 and so on. For the nth year then would be A is equal to P times 1 plus R to the power of n. So we're going to use this formula to find the amount of A. So in this case, suppose that the principal of P dollars is invested at an annual interest rate of R. We're going to change R to the decimal always. Compounded n times per year. Then the amount A accumulated after T years is given by this formula. So this would be an example where we can use that formula. Here in this case, we have $1,000 to invest at an annual 1.5% compounded quarterly. That means 4 times per year. How much will be the amount after 10 years if no withdrawals are made? How much interest is earned? So we're going to use the formula here. Let's see what we have. We know P is equal to 1,000. Rate is equal to 1.5%. You divide 1.5 by 100, you get 0.015. We change it to decimal. N is 4 because this is compounded quarterly. And T is equal to 10. So we're going to use our formula, basically substitute the values, and we can solve for A. So A would be equal to 1,000 times. It would be a good idea now for those of you watching this later at home, grab your calculator, see if you can come up with this same number here inside the parentheses, and then raise it to the power of 40 multiplied by 1,000. You can see it would be about 1,161 0.51. So the interest earned subtracted from 1,000 would be 161.51. We could use your graphing calculator to obtain the same result when you graph this function here and evaluate that x is equal to 10, and as you can see, you can get the very close number here as it even more accurate. The natural number e. The e is a constant which is equal to this number here, about 2.7, and then all these numbers after that. If an amount of p dollars is deposited at a rate of interest r, we're going to change r to the decimal of it, is compounded continuously now for t years, then we want to find the amount in dollar. We can use this formula. A is equal to P times e to the power of RT. So this would be an example where the $1,000 is invested in an account paying 1.5% compounded continuously for 10 years. We want to find the total amount of deposit at the end of 10 years. I'm going to also compare this with the previous example that we did earlier. So we have the P, and the rate is 1.5 divided by 100, again is 0.015. The time is the same. Now we're going to use this other formula. A would be equal to, all the information are given to me, and when you calculate this, you get $1,161.83. After 10 years, the amount contains this amount, which is subtracted from 1,000 would be 161.83. So if you compare that with what we did previously, looks like it is greater using continuous compounding. And we can also use our graphing calculator to obtain the same result. Once we enter the equation here, y1 is equal to 1,000 e to the power of 0.015x, and then at x equal to 10, as you can see, we can get the same amount that we calculated. This would be another example where we can use an exponential function. The chances of dying from heart disease increase potentially after age 40 according to this function. So this is given to me, where r is the risk. They're giving you that in terms of decimal at age 40, and x is a number of years after 40. So we'll compare the risk at age 75 with the risk at age 40. So in this example here, we're going to find the age difference here. 75 minus 40 would be 35. So we want to find f of 35, where f of x equal to r times 1.11 to the power of x. Now x is 35, so you can see for the time difference would be 38.6 r. So what that means is the risk is almost 39 times as greater at the age 75 as opposed to age 40.